Hello, good friends. Today we're going to unpack how small language models can master mathematical reasoning through self-evolved deep thinking. We'll explore a fascinating research paper titled rStar-Math Can Master Math Reasoning with Self-Evolved Deep Thinking, authored by researchers from Microsoft Research Asia. Traditionally, large language models, or LLMs, have been the go-to for tackling complex tasks, including mathematical problem-solving. These models are massive and require considerable computational resources. But what if smaller models could achieve similar or even superior performance without relying on larger counterparts? This is precisely what the rStar-Math approach accomplishes. In conventional methods, language models attempt to solve math problems by generating complete solutions in a single step. This approach is akin to what psychologists refer to as System 1 thinking, fast, intuitive, but susceptible to errors. The researchers propose a shift towards System 2 thinking, involving deliberate, analytical, and step-by-step reasoning, similar to the careful process humans use when tackling complex mathematical challenges. At the heart of this approach is Monte Carlo tree search, or MCTS, an algorithm originally developed for decision-making in games like chess and Go. By exploring possible moves and outcomes, MCTS finds the most promising path forward. In mathematical reasoning, it allows the model to consider multiple steps, systematically breaking down complex problems into simpler parts to arrive at the correct answer. The researchers introduced three key innovations to enhance the capabilities of small language models, or SLMs, in mathematical reasoning. First, they developed a novel method for generating training data called the code-augmented chain of thought, or CAUT. This technique involves performing extensive MCTS rollouts to create detailed, step-by-step reasoning trajectories that are verified for correctness. By augmenting the reasoning process with code, the model learns from high-quality examples that include both the natural language reasoning and precise computations. This ensures a robust understanding of mathematical concepts and helps the model develop accurate problem-solving skills. Second, they introduced a process preference model, or PPM. In previous approaches, assigning exact scores to each reasoning step proved to be unreliable and labor-intensive. The PPM addresses this by using preference pairs. Instead of assigning a numerical score to each step, the model learns to prefer one reasoning step over another based on which leads closer to the correct solution. This method simplifies the training process and allows the model to develop a more nuanced understanding of effective problem-solving strategies without the need for precise scoring. Third, they implemented a self-evolution process. Beginning with basic models, they iteratively refined both the policy SLM, the model that generates the reasoning steps, and the PPM over multiple rounds. In each round, the models generated new training data, learned from it, and improved their reasoning abilities. This iterative self-improvement enabled the models to tackle increasingly difficult problems, effectively teaching themselves to think more deeply and accurately. The results of this approach are noteworthy. On the math benchmark, a standard set of mathematical problems used to evaluate AI models, rStar-Math significantly enhance the performance of small models. For a model with 7 billion parameters, The accuracy improved from 58.8% to 90.0%. Similarly, a model with 3.8 billion parameters saw an increase from 41.4% to 86.4% accuracy. These improvements not only demonstrate substantial leaps in performance, but also surpass the results achieved by larger models like OpenAI's O1 Preview. Furthermore, on the American Invitational Mathematics Examination, AIME, which features problems used in the USA Mathematical Olympiad, rStar-Math solved an average of 53.3% of the questions. This performance places the models among the top 20% of high school students participating in these competitions, highlighting their advanced mathematical reasoning capabilities. An intriguing observation from the study is the emergence of self-reflection within the models. During problem solving, the models began to recognize when a particular line of reasoning was unproductive and would backtrack to explore alternative approaches. This self-correcting behavior was not explicitly programmed, but emerged naturally from the deep thinking processes fostered by MCTS and guided by the PPM. It mirrors the way humans reconsider and revise their thinking when faced with challenging problems. So, what does all this signify? The rStar-Math approach demonstrates that small language models can, through innovative training techniques and self-evolution, achieve and even surpass the mathematical reasoning capabilities of much larger models. By employing deep, systematic thinking and iterative self-improvement, these models become more efficient and effective without necessitating vast computational resources. This advancement has meaningful implications for the future of artificial intelligence. It suggests that powerful AI tools can become more accessible and cost-effective, broadening their applicability across various domains. By unlocking the potential of smaller models, we can make sophisticated AI technologies available to a wider range of users and applications. Thank you for joining me on this enlightening exploration of rStar-Math and the strides being made in self-evolved deep thinking within AI. It's been a pleasure discussing these innovations with you, and I hope it has sparked your interest in the dynamic and ever-evolving field of artificial intelligence. Until our next conversation, take care and keep nurturing your curiosity.